So in this lecture, we'll talk about an estimator for the linear regression equation that we introduced in lecture 1. In lecture 1, we introduced this linear regression equation and we discussed the interpretation of the linear regression equation. So we said that the interpretation of this equation, including the interpretation of the coefficients, and the interpretation of the whole observable part of the equation. These interpretations depend on the purpose of our research. If the purpose is descriptive, if what we want to do is to describe the joint distribution of the y and x variables, or conditional distribution of y given the x variables, then we might consider models that summarize this conditional distribution, for example, the conditional mean model or the linear projection model. If we think that the conditional mean of y given the x variables is linear in these x variables, then we can let u, the error term, to be equal to y minus ey given x. And this observable part of the equation will describe the conditional mean of y given x1 to xk. And these betas will measure how much the conditional mean changes when x1 changes, right? How much y changes on average when, say, x1 changes, holding the other x variables constant. If the conditional mean is not linear, if we do not believe that the conditional mean is linear, then we can define u to be y minus the linear projection of y on x1 to xk. And this observable part of the linear regression equation describes the linear projection of the conditional mean function on x1 to xk. What is the linear projection? The linear projection is a linear function of the x variables that are that is the closest to the conditional mean among all the linear functions of the x variables. So, and the closeness is measured by the mean squared error, right? expected value of the square of the difference between the conditional mean function and this linear function. So linear projection is an approximation of the conditional mean when the conditional mean is not linear. If our purpose instead is to infer causality, so instead of just trying to describe the conditional distribution of y given the x variables, we want to study the causal effect of the x variables on y. If that is our research purpose, then we're gonna need to tell a story about how y is generated. And in that story, we want the x variables to play a role, potentially. And in that story, there may also be other factors that also play a role in the process in which y is generated. Now the error term u will be a summary of the other factors, the factors that we are not including in the x variables that also participate in generating y. So all of those interpretations are based on the true values of the parameters. These true values of the parameters, these betas, in practice are unknown. And we try to estimate them based on the data. So the main goal of econometrics is try to estimate the unknown parameter values using data. So the first step is to get a data set. There are many different kinds of data sets, but in this course, in 704, virtually all the data sets that we will encounter are of this particular type. They are cross-sectional, random samples of a population. So cross-sectional means that the data, all the points in the data set are collected at roughly one point of time. For example, the data collected during the 2010 US Census, they are all collected in 2010. Then what do we mean by random sample? So random sample is a collection of individuals randomly drawn from a population. For example, 1,000 randomly drawn adult men from all adult men in the US. And what about a population? A population is the collection of all the individuals that are relevant for our research. So suppose we want to know the expected hourly wage for adult men in the United States, then all the adult men in the United States, for example, in 2010, would be the population that we are studying. So a random sample is randomly drawn from the population. So that basically describes the majority of the data sets that we will encounter in this class. Now a bit of notation. Random variables for an arbitrary member, a random member in the population, are denoted by this y, the x variable, and the u variable without the subscript I. So without subscript I. So a random, arbitrary random member from the population is not indexed. We do not attach a number to it. So we describe their characteristics by these random variables without the subscript I. So let's say this is the population of Hello Kitties in an arbitrary member of the population. Say this one, it doesn't have a number. And the characteristics of this arbitrary member of the population is denoted by these symbols without the I in subscript. On the other hand, we will add a subscript to these random variables if we take these random variables to be the characteristics of the ith member of a sample. So suppose in this population of Hello Kitties, you draw a sample, in this case, say of size n, then this is the first draw that you have. This is the second draw. Say this is the ith draw, this is the I plus 2th draw, and this is the nth draw. Then each of the individuals in the sample are numbered. So the characteristics of each of the individual is denoted by these random variables with a subscript. This subscript is the index for the individual you are referring to. So for the ith individual, the characteristics of that ith individual will be yi x1i to xki to ui. So characteristics of an individual is basically any random variables that are attached to that individual. For example, income of the individual, education of the individual, and say height and weight of the individual, etc. So that's a notation about population random variables and sample random variables. And if the sample is a random sample, it's a randomly drawn sample from the population, then these random variables with the I subscript have the same distribution as the population random variables. They have the same distribution. A sample of size n is denoted by this collection of characteristics for this I from 1 to n individuals. And this is our data set that we use to estimate the beta parameters. The regression equation that we introduced were written in terms of the population random variables, so there were no I subscript. Now, if you specialize the regression equation to each member of the sample, you can add the subscript to the random variables involved. So this is the same regression equation, linear regression equation that we introduced, except that we now specifically refer to the ith individual. So this is the equation for the ith individual. And we would like to estimate the unknown parameters betas using the random sample. So how do we estimate this? Before we introduce the estimator, I want to stress a notation. Just to emphasize, our unknown parameters are the betas without a hat or subscript n or anything. And their estimators are the betas with the hat added. So we use the hat to denote estimators. So the unknown parameters are denoted usually by beta or sometimes theta. And in the first part of the course, we also used maybe mu or lambda. These are all notations for the parameters. Here in linear regression is usually just beta. Beta is a parameter. It is an unknown number. It is non-random. On the other hand, we use beta hat as a notation for the estimator for beta. And beta hat is a random variable. So beta is the non-random target that we want to estimate. Non-random unknown parameter value. Beta hat is an estimator for beta, and it is a random variable. It is a random variable because it is a function of the random sample, our data set. And from the ex ante point of view, the random sample is a collection of random variables. Therefore, the estimator is a random variable. So now let's introduce the estimator. And the estimator we are going to introduce is called the ordinary least squares estimator. So ordinary least squares estimator, or OLS estimator. Now let me straight off the bat give you the definition of the ordinary least square estimator. The estimator is defined to be the argument of this function, which we call the criterion function. So the least squares criterion function. So what's argmin? Argmin means that is the solution to the min, the solution to the minimization problem. So the beta hats are the minimizers of this least square criterion function. So what is the least square criterion function? The least square criterion function takes each yi and use a linear function of the xi's to approximate it. And the approximation error is then squared. So for each I, we take the square of the approximation error on y for y when we use a linear function of x to approximate it. And we sum up all the approximation errors, all the squares of all the estimation errors, and take that as the criterion function to minimize. So in a sense, the OLS estimator, the beta hat, gives us the best linear approximation for y. And the best is measured by sum of squared approximation errors. So just to graphically demonstrate what this means, let's say in this graph, the horizontal axis is x. Now we have only one x variables, k equals 1. There is only an x1. And so that is x1 and that is y. And our data set is yi x1i. So that's x1, I from 1 to n. So it's n pairs of yx. So let's say this is these points are the data set. So that is the data set. Each point is for an individual. Let's say this point is yi xi. Or maybe I should write xi yi because x is plotted on the horizontal axis. Clearly, these points are everywhere. There isn't a straight line that goes through every point. You draw a line, for example, I draw a line here. It goes through some points, it goes through these ice points. It's close to some points, but it's kind of far away from some other points. So like this point has a very large vertical distance from the line. Now, so that is a line. It can be written as y equals some b naught plus some b1 value x1. And this has approximation error because there are many points that are not on this line. So that's the approximation error, vertical error. And every point has an approximation error to this line. And if you square all of these line segments and add them up, and that is your least squares criterion function. Does this line minimize that sum of squared differences? Well, this line doesn't. You can draw another line. This one has a different set of approximation errors. Therefore, it has a different least square criterion function value. This line is also not optimal. This, for these points, is the optimal line. It minimizes the sum of the square of these approximation errors. So as you can see, it's kind of reasonable because it's close to many points. And it's far away from that point, but you can't really tilt that way. You can't really tilt that way because if you tilt that way, you're going to be further away from these points. And it's far from this point also, but you also cannot tilt closer to that way because otherwise you will be much further away from those points. So this line strikes a balance. It minimizes the sum of the squares of the approximation error. Now on this graph, so this approximation, this optimal line is defined, can be denoted by the beta hats. So this optimal line is beta 0 hat plus beta 1 hat x. And on this graph, I also want to show you this error, this approximation error. See, let's say this is the ith point. Then this vertical distance between the ith point and the approximation line, the optimal approximation line, that difference. So this level is for yi, so that's the yi's level. And this is the beta 0 hat plus beta 1 hat xi or x1i. And this difference is the length of the difference is absolute value of u hat, which is the absolute value of yi minus beta 0 hat plus beta 1 hat x1i. So where ui hat is defined to be this approximation error yi minus beta 0 hat minus beta 1 hat x1i in this example. And that is called the residual. That is the OLS residual. And therefore, the sum of the squares of the approximation error is also called the sum of squared residual. So here on this slide, I'm repeating what I just said. Okay. So this estimator we just defined is called the ordinary least squares estimator. It minimizes the sum of the square of the residuals. So sum of the squares of the residuals. Now we know what the OLS estimator is defined to be. We want to solve for an explicit formula. We want to solve this minimization problem and see what beta hat should equal to. To solve this, we look at this criterion function we're trying to minimize. This function is a convex function because the quadratic function is a convex function. So a convex function looks like this. So it is a convex function. And also, it is differentiable because it's a square function. Square function is differentiable. It's a square of this linear function of b. Both square and linear functions are differentiable. Therefore, this whole criterion function is differentiable by the chain rule, right? So it's a convex differentiable function or differentiable convex function. To solving the minimization of a convex differentiable function is easy. We can do this by the first order conditions. First order conditions are necessary and sufficient for solving this convex differentiable function, for minimizing this convex differentiable function. So let's try to solve this by the first order conditions. Let's first derive the first order conditions. To derive the first order condition, we take the first derivative of the criterion function with respect to each of these parameter values and set them to 0. And the beta hats, the solution to that minimization problem will be the values of b that solve those equations. So first we take the first derivative, right? So we start with b naught. We can start with the first parameter, b naught. So the derivative of a sum of two functions is equal to the sum of the derivative of the two functions. So the first derivative is sum I from 1 to n. And then to take derivative of this square, we can, with respect to this b naught, we can use the chain rule. First, we take derivative of the square function. That gives us 2 times what's inside the square function. And then what's inside the square function is a linear function of b naught with the coefficient -1. So the chain rule tells us that we should multiply -1. So that is the first derivative of the criterion function with respect to b naught. And now let's take the derivative with respect to the other points, other b's as well. So we can do b1 next. For b1, the derivative is similar, so it's sum 2 times what's inside the square function times the coefficient on b1 for this function inside the square bracket. The coefficient on b1 is minus x1i. So that's minus x1i. So that's the derivative of the least square criterion function with respect to B1. And we can keep doing that until we're at the last unknown parameter. And the derivative with respect to that, to bk, is yi, is this sum 2 times what's inside the square function. So I forgot to put a bracket around this linear function. bk xki times minus xki. So these are a system of k plus 1 linear equations with k plus 1 unknown parameters. And the optimal value solves this system of equations. So the solution, so the b's that satisfy these equations are the betas. So just to be clear about that point, we replace all the b's by their optimal value. So just to be clear that the values of b that solve these equations are the optimal values, are the beta hat. All right. Before solving this system of equations, I want to simplify it a little bit. Now notice that this constant multiplier doesn't matter, so I can cancel those out without affecting the solution to the problem. And I can also cancel out this minus sign, so that also doesn't affect the solution. So after these simplifications, we arrive at this system of equations. Now we can actually try to solve these equations from here. But before solving these equations, I want to digress a little bit and talk about a property that the regression residue has. Notice that this is defined to be ui hat, the regression residues. So this difference is the definition of ui hat. We can then replace all of this by ui hat. So that is ui hat. We can replace all of this by the ui hat. And we get the following property or feature of the regression residue. That is, the sum of the regression residue equals 0. And this, you can verify, is the covariance. It's covariance times n. Sorry, covariance times n. That's the sample covariance. Between ui hat and x1i. That's the sample covariance of ui hat. So divide that by 1 over n, then it is the sample covariance. And dividing it by n, by the sample size n, doesn't affect the equation. So the sample covariance of ui hat and x1i equals 0. Same thing happens for all the x variables. So the sample covariance of the regression residual, OLS regression residual with all the x variables are zeros. So this is a feature, an interesting feature of the OLS regression, OLS residue. So the residue has a sample mean 0. Sample mean of the OLS residue has mean is 0, and the sample covariance between, or sample correlation between the regression residue with any of the included x variables is 0. Notice that these equations are derived simply from the first order condition. This is an immediate implication of the first order condition. and the first order condition is an immediate implication of the definition of the OLS estimators. And so these equations are actually features of the definition of the estimator. It actually has nothing to do with what we assume on the model itself. These are direct implication of the definition of the beta hats, the estimators, and the regression residual. And these do not imply and does not require, so these do not require, say, the random variable u, the error term, to satisfy mean zero, or EU given x or EU times x for any of the x to be zero. So this does not require the error term to satisfy any of these conditions. So it has, so these features has no implication whatsoever on what the error term u is assumed to satisfy. It's a direct, so these are only implication of the OLS estimator. Okay, so that's kind of important to know. Just don't get confused about the residual and the error term. Okay, so u hat regression residual, and ui without the hat is the error term. So OLS regression residuals always satisfy these equations, regardless of what assumptions the error term ui satisfies. Okay. So that's a digress. I consider that kind of an important digress. But now let's solve for the ordinary least square estimator. In order to solve for the ordinary least square estimator, we actually want to bring in some simplifying notation. And the simplifying notation requires some matrix algebra notation. If you have learned matrix algebra before, then this part of the lecture will be a review. If you have not, don't panic, because we don't need too much of the knowledge from matrix algebra. And pretty much everything that we need will be covered in the this slide and the next few slides. So just pay attention now, then that will be mostly sufficient. So we're gonna define a column vector. A column vector is a bunch of numbers arranged in a column and written in between a pair of round brackets, like this one. 1, 0, minus 2, these three numbers arranged in a column written in a pair of round brackets. That is a column vector. And this column vector is of length 3, and the length of the column vector is the number of numbers that you arrange in the column. Here there are 3 numbers, therefore this column vector has length 3. So that's the definition of a column vector. And what about a row vector? We can also define a row vector, which is similar to the column vector. It's a bunch of numbers arranged, but now in a row instead of in a column. And also we write it in between a pair of round brackets. So for example, this is a row vector, and it's 3 numbers arranged in a row. And this row vector has length 3 because it contains 3 numbers arranged in a row. Now I want to explain this notation. So the arrow, especially the arrow on top of the symbol, this arrow arrow, not error. This arrow on top of the symbol stands for vector. So a letter with an arrow on top means vector A. So A with the arrow on top is vector A. So the vector A, this vector A is this column vector. And here, this notation, we have vector A with a prime on it. So that is read as vector A prime. Vector A prime is the transpose of the vector. So what is vector transpose? The transpose of a column vector is the vector lying down, and transpose of a row vector is the vector standing up. So we have a vertically arranged bunch of numbers that's a column vector. If you lie it down, that becomes a row vector, and that row vector is the transpose of the column vector. And if you start with a row vector, a bunch of numbers arranged in a row, you stand it up, then that becomes the column vector. And that column vector is the transpose of the row vector. We use the prime on top of the vector to denote the transpose. So for example, this column vector transposed becomes this row vector. So the transpose is composed of the same numbers arranged in the same sequence, same order, but instead of in a column, now in a row. And the transpose of the row vector is a column vector, so it's the same idea. So the transpose contains the same numbers arranged in the same order, but instead of in a row, now in a column. Clearly, by the definition of transpose, when you apply the transpose a vector twice, then you get the original vector back, regardless of whether the original vector is a row or column vector. So that's vector transpose. We can also define vector addition. So since vectors are a bunch of numbers, we can add numbers up. We can also add vectors up. Vectors of the same length and shape can be added up. If two length 3 vectors, if they're both column vectors, they can be added up, and the sum is also a column vector. Two row vectors of the same length can also be added up, and the result is a row vector of the same length. And the sum is element-wise sum. So the first element of the sum of the resulting vector is the sum of the first element of the two vectors you're adding up. And similarly for the second, similarly for the third, and so on and so forth. So that's vector addition. We can also define scalar multiplication. That is, we can multiply a vector by a number, which is also called here a scalar. So a scalar is just one number. You can multiply a scalar to a vector, and that simply means you're multiplying the scalar to each and every element of the vector. So 3 times 1, 0 minus 1 vector equals 3, 0 minus 3 vector, equals the vector composed of 3, 0 minus 3. And that clearly also equals 3, 0 minus 3, the row vector transpose. And the row vector is 3 times 1, 0 minus 1, then transpose. So as you can see, the transpose of this vector, so what I'm demonstrating is that the transpose and scalar multiplication can be exchanged. The order of these two operations can be exchanged. So you can do the scalar multiplication first and then transpose. You're going to get this column vector. Or you can transpose it and then multiply by the scalar, and you get the same column vector. So what that says is if you have a scalar A times a vector A, and then you transpose it, that equals A times vector A transpose. Now, we not only can multiply a scalar to a vector, you can also multiply a vector to a vector. But you have to be careful which vector is put on the left and which vector is put on the right. So multiplication of vectors can be defined in two ways. The first way is when a row vector left multiply a column vector of the same length. When a row vector left multiply a column vector of the same length, the product is well defined and the result is a scalar. And that scalar equals the sum of the product of these corresponding elements of the two vectors. So that basically equals 1 times 2 plus 0 times 1 plus minus 1 times 0, which is 2 in this case. So that's how you multiply vectors. So a row vector can left multiply a column vector, and the result is a scalar. And if you have two column vectors, A vector and B vector, they are of the same length, you can define their inner product. The inner product is defined for two column vectors, and their inner product is A vector prime times B vector. So A vector prime is a row vector. So now you have a row vector times a column vector. And that is well defined, and the result is a scalar. So the inner product of this column vector and that one is 2. So, and you can also multiply two vectors in a different way. You can also put the row vector on the right when you multiply it to a column vector. When a row vector right multiply a column vector, the result that can be well defined, and the result is a matrix. So what is a matrix? A matrix is a bunch of numbers arranged in a rectangular form, written in between a pair of round brackets. So just like vectors are a row of numbers or a column of numbers, a matrix is a rectangle of numbers written in between a pair of round brackets. If you let a row vector right multiply a column vector, the result is a matrix. For example, if you do this, put the row vector on the right and the column vector on the left, then the result is a matrix where the first element, first row, first column is given by the product of the first row of the one on the left times the first column for the vector on the right. So that's 1 times 2. And first row, second column is obtained by multiplying the first row to the second column. And similarly for the first row, third column. There isn't a first row, fourth column because there is no fourth column for the vector on the right. And how many rows are there? That depends on how many rows you have for the vector on the left. So for the second row, you can have 0 times 2, 0 times 3, 0 times 4. And -1 times 2, -1 times 3, -1 times 4, 2 times 2, 2 times 3, 2 times 4. So that will be the matrix obtained from right multiplying a row vector to a column vector. As you can see, these two vectors do not need to have the same length. This multiplication is defined whether or not the two vectors have the same length. Now, if you have two column vectors, vector A and vector B, same or different length, their outer product is defined to be vector A times the transpose of vector B. So that is their outer product. Remember their inner product, just compare it to inner product is vector A transpose B. Now, both vectors A and B are column vectors. The inner product is only defined when the same length, when the two vectors are of the same length. And the result is a scalar. And the outer product is defined when they either have same or different lengths, and the result is a matrix. So that's outer product and matrix. Now let's talk about some basic concepts about the matrix. First is matrix size. The size of a matrix is a pair of numbers. The first number in the pair is the number of rows, and the second number is the number of columns. For example, this matrix has 3 rows and 2 columns, so therefore the size is 3, 2. And this matrix is called a 3 by 2 matrix. You can also transpose a matrix. Transposing a matrix turns the rows into columns. First row becomes the first column, second row becomes the second column, and third row becomes the third column. You can also look at the columns. The first column also becomes the first row. And the second column becomes the second row when you take the transpose. Just like adding up vectors, you can also add up matrices, but they need to be of the same size. When two matrices are of the same size, you can add them up, and the sum is obtained by element-wise addition. So the sum is a matrix of the same size, and each element is obtained by adding up the corresponding elements of the two matrices we're adding up. So that's 2 plus 1, 3 plus 0, 0 plus 0, 0 plus 1, 1 plus 1, 0 plus 1. So you get this matrix as the sum. So that is 3, 3, 0, 1, 2, 1. So you can add up matrices. You can also scalar multiply a matrix. You can multiply a scalar to the matrix. What you're doing is basically multiplying the scalar to each and every element of the matrix. Okay, so that equals 2 times 2, 2 times 3, 2 times 0, 2 times 0, 2 times 1, 2 times 0. So that is how you define scalar multiplication. As you see for matrix and vector products, which matrix, which vector is put on the left and which on the right is important, as you can see from at this point. But when you multiply a matrix or scalar to a matrix or vector to a scalar, the scalar can be either on the right or on the left. It doesn't matter. It means the same thing. Whether you put it on the left or put it on the right, it doesn't matter. So that doesn't matter if you're multiplying something to a scalar. All right, so now something a little bit more complicated. We can also do matrix multiplications. That is, we can multiply a matrix to another matrix. A matrix A can left multiply a matrix B if the number of columns for the first column for the first matrix is the same as the number of rows for the second. So if the column and the row match, number of column, number of row match for the two matrices, then A times B is a conformable matrix multiplication. That is, it is a well-defined matrix multiplication. And the resulting matrix is of size M times C, where M is the number of rows for the first matrix and C is the number of columns for the second matrix. For example, let's say this is A and this is B. We can do this multiplication in the following way. So to do matrix multiplication, to obtain the first element, first row, first column of the product matrix, we're going to take the first row of the matrix on the left and multiply it to the first column of the matrix on the right. We take that and multiply it to this. That's the first row, first column of the resulting matrix. If the matrix on the right has a second column here, then the resulting matrix is also going to have a second column. And the second column, first row, will be obtained by multiplying the first row of the matrix on the left to the second column of the second matrix, of the matrix on the right. If you do this multiplication, the number you get will be put on in this location, the first row, second column. And in this example, there isn't a second row, so the resulting matrix doesn't, there isn't a second column for the matrix on the right, so the resulting matrix doesn't have a second column. So it stops at the first column. But the matrix on the right has a second row, so therefore the resulting matrix also has a second row. Second row, first column will be the second row of the matrix on the left times the first column of the matrix on the right. So that should be 0, 1, 1, 1, 0, minus 1. And we already know how to multiply a row vector to a column vector of the same length. So that is 1 times 1 plus 1 times 0 plus 0 times minus 1. So the first element is 1. Second element is minus 1. So a 2 by 3 matrix times a 3 by 1 matrix gives us a 2 by 1 matrix. So that's how you do matrix multiplication. I want to emphasize that the order of multiplication for matrices is very important. AB in general is not equal to BA. So AB, sometimes the matrix product AB is conformable and BA is not conformable. For example, if this is A, this is B, then AB is conformable, but B, if you move this to the right, then that multiplication is not conformable because this 1 is not equal to 2. So clearly in that case, AB is not equal to BA. And sometimes both AB and BA are conformable, but they are of different size, so they're clearly also not equal. But I want to emphasize, even when both are conformable, and if they are of the same size, they are still, in general, not equal. Just to give you an example, now suppose we are multiplying these two matrices. Those are 2 by 2 matrices. So AB and BA are both conformable and both give you a matrix of 2 by 2. So, but their product are not the same. So you can calculate this matrix product, which equals, say, 1, 1 times 0, 1. That will give you the first row, first column, and that is 1. And if you multiply 1, 1 to the second column, 1, 1, 0, 0, that gives you first row, second column, and that is 0. You do the same thing for the second row of the first matrix, second row, first column, that gives you 1. You put it in the second row, first column of the product. And second row, second column gives you this element, which is 0. But if you switch the order of multiplication, you write 0, 0, 1, 0 on the left, but you write 1, 1, 0, 1 on the right, then what are you going to get? What you will get is actually the following. You multiply 0, 0 to 1, 0, and that's the first row, first column. That is 0. And if you multiply first row to the second column, that's also 0. When you multiply the second row to the first column, that becomes the second row, first column in the product matrix. So that is 1. And similarly, this is also 1. These two matrices are not equal. Clearly, they are not equal. So when you do matrix multiplications, the order of multiplication is very, very important. Now I want to introduce a concept called positive definite matrices. First, I want to introduce square matrix. What is a square matrix? Well, a general matrix is a rectangular form of numbers, a rectangle. If that rectangle is a square, so square is a special case of rectangle. If that rectangle is a square, then that matrix is a square matrix. So that is, if the number of rows and the number of columns are the same, then the matrix is a square matrix. A square matrix is symmetric if the transpose of the matrix equals itself. So that's quite self-explaining. This is an example of a symmetric matrix. A symmetric square matrix is positive semi-definite if for any column vector A of the same length as the number of column or number of row of the square matrix, for any column vector A prime vector A prime times matrix A times vector A, that matrix product is non-negative. If this matrix product is non-negative for any and all column vectors A, then the matrix A is called positive semi-definite. And a positive semi-definite matrix is positive definite without the semi. If this product is strictly positive for all column vectors A that are not the zero vector. Clearly, if A is the zero vector, then this product equals 0. But if the matrix is positive definite, then this is strictly positive whenever A is not composed of all zeros. So I can give you a couple of examples of I can give you an example of a positive semi-definite matrix. So for example, this matrix is positive semi-definite. How can I tell that it is positive semi-definite? So it is, if you take a vector A that equals A1, A2, then this product equals A1, A2, 1, 0, 0, 1, 0, 0, A1, A2, and that equals, so we can first multiply these two together, and we get, so the first row, first row, first column will be A1, A2 times 1, 0, so that's A1. First row, second column is A1, A2 times 0, 0, that's 0. Then times A1, A2, and that becomes A1 squared. That is clearly always non-negative, whatever A1, A2s are. This is not positive definite because you can find an A vector that is not a zero vector, say 0, 1, then vector A prime, matrix A, vector A equals 0, equals A1 squared, which is 0. It is not strictly positive. So therefore, this matrix is not positive definite. All right, so one last concept is matrix inverse. Before defining matrix inverse, I want to define the identity matrix. The identity matrix is a symmetric positive definite square matrix of the following form. It's a square matrix where on the diagonal of the matrix, so a diagonal of the matrix, you have all ones, and in the off diagonal locations, you have all zeros. If a matrix is of this form, then it is an identity matrix. So for example, two-dimensional identity matrix is 1, 0, 0, 1. An identity matrix multiplying any other matrix as long as the product is conformable, you get that matrix back. So for any matrix A, regardless of whether you right multiply it or left multiply it, as long as the product is conformable, you get the same matrix back. So as you can see, so that's why it's called an identity matrix. Multiplying anything will give you an identical number, identical matrix as before. So you can verify that with an example, say 1, 0, 0, 1 times anything, say 1, 2, 3, 4, and you get the same matrix back. So 1, 0 times 1, 3, that's 1. And 1, 0 times 2, 4, that's 2. And 0, 1 times 1, 3, you get 0 times 1, 1 times 3, that's 3. And 0, 1 times 2, 4, that is gives you 4. So you get the same matrix back. So now we can define matrix inverse. A square matrix A can be inverted or is invertible if there exists another matrix, which we denote by A to the power minus 1, such that A times A to the power minus 1 and A to the power minus 1 times A equals the identity matrix. And that matrix is called the inverse of A. So now positive semi-definiteness and positive definiteness is also related to inverse, to matrix, to the invertibility of the matrix. A positive definite matrix is invertible, but a positive semi-definite matrix, if it is not positive definite, then it's not invertible. So for example, 1, 0, 0, 0, as we have shown, is a positive semi-definite matrix. It's not a positive definite matrix. It is not invertible. Why is that? Because you can multiply it to any arbitrary matrix, say A11, A12, A21, A22. Multiplying it to any arbitrary matrix, you are going to get something that cannot be an identity matrix. So when you work through the multiplication algebra, you find this is A11, A12, 0, 0. Whatever the A's are, you cannot make this an identity matrix. Why so? Because the second column, second row is always 0, and that's not the same as what an identity matrix would have in this location. So this cannot be the identity matrix, regardless of what matrix you put here. So positive semi-definite but not positive definite matrix is not invertible. So now that we have the secret of the matrix, we can do amazing things with it. And we can solve the ordinary least square first order conditions in a simple way. How do we do that? Let's start with the first order conditions. Okay, the first order condition, this is the first order condition, the one with respect to B naught. We start with this and we want to write it in matrix language. How do we write it in matrix language? So first, notice that this is the inner product of two vectors. So it is this vector, beta 0 hat. Sorry. So this is the beta 0 hat, beta 1 hat, beta k hat. So this is the row vector times the column vector 1, x1i, xki. Right? So this equals the product of these two vectors. Now, if you define the beta hat vector to be this column vector, so here there is a typo, so that's beta 0 and that is beta 1. Okay. If you define the beta vector to be this column vector, and you define the x vector, xi vector, as this column vector, then this sum, this linear function of the x, can be written as the inner product of the two. Can be written as x vector prime times beta hat vector. And therefore, this first order condition becomes sum of yi minus this inner product equals 0. Right? So because this is the inner product of these two vectors that we have just defined. So written in vector notation, this equation is much shorter. It's very short. Now, clearly we can do that for all the other first order conditions as well. So this is the first order condition with respect to B1. And we can replace this by yi minus xi vector transpose beta hat vector. Times x1i. Okay, you can do that. So that becomes this. And now realize that x1i is a scalar. It's x1 is this one random variable for the individual I. So that is a scalar. And yi is also a scalar. This inner product is also a scalar. So this is actually a scalar times a scalar. When these both are scalars, say 2 times 3, you can exchange the order of multiplication equals 3 times 2, right? So everybody agrees. And you can change the order of multiplication, so that scalar multiplication equals this. And you can write x1i on the left, and that's not going to change the product because both of these are scalars. So that can be that first order condition can be written in this way. So this first order condition can be written in this simple short form. Now you do that for all the b's except the b naught. You do that for all the b's, you're going to get this simplification. Now you put them all together. This is the first order condition for b naught. This is for b1, and this is for bk, and so on and so forth. Okay, so you already have simplified the equation system. Now we are going to simplify it even further. Now we can write it in terms of a vector. That is, we put these k plus 1 numbers into a vector, a k plus 1 length, k plus 1 column vector. Every element being 0 is equivalent to the whole vector equals a 0 vector, right? So now we write it in a big vector form, and the system of equations become this vector equals the 0 vector. So this boldface 0 is a vector of zeros. And here there are k plus 1 zeros arranged in this vertical form. Okay. So this first order condition can be written in this vertical form, in this vector form. And summation is simply addition, right? Summation is just addition. We are adding up all these scalar numbers for I from 1 to n. We're adding up the n of this. Okay, so this is actually a vector addition result. But what are we adding up? We are adding up these vectors. Okay, if you put this k plus 1 numbers for each I into a vector, then this vector is the addition, is the summation of these vectors. So again, equivalently, we can write the first order condition as the sum of these vectors equals 0. And we're getting very close to the solution now. What we're going to do next is to multiply this 1 to yi and to this x vector prime beta hat vector, just to multiply it inside, and multiply the x1i also inside, and do this for all of these elements in this k plus 1 vector. So we do that. Actually, I'm sorry, I take it back. So what we are going to do next is to recognize that this is common. This is a scalar. So this is a scalar, and it is common across all the elements of this vector. So what do we say? We can factor out this scalar. So because that is a scalar, we can factor it out. So this vector is actually equal to a scalar multiplication of this vector. Notice because this is a scalar, it doesn't matter whether we put it on the left or on the right. We are going to put it on the right because that's going to facilitate what we do next. So the first order conditions becomes this form. Now recognize what is this vector. That is the xi vector that we defined. So this vector is xi vector, the same xi vector that we defined in a few slides ago. So we can use that notation and write that as xi vector times this residue equals 0. So we have written the first order condition equation system into this form. So this is a lot shorter than before. So this is a very simplified form of the first order condition, and that's going to lead to our solution. So what we are going to do next is to distribute this vector to these two terms that we are adding up. Okay, so the distributive rule still works for vectors and matrices as long as the product is conformable. So we can distribute it to these two terms. And we get this sum of xi vector times yi minus xi vector times xi vector prime times beta hat vector. Now the sum of the difference is also equal to the difference of the sum. Okay, so we just basically what we are doing is to collect all the terms that are of the form x times y. And we also collect all the terms that are of the form x times beta. And that gives us this term. So that implies this sum of x vector times y minus sum of x vector prime times beta hat vector equals 0. Now what we do is to move this to the other side of the equation, and also realize that this beta hat is common across all the i's, so it doesn't depend on I, so it can be factored out of the summation. This beta hat vector can be factored out of the summation because it doesn't have an I subscript. So what we have gotten is this. Notice that what's important is this doesn't have a subscript I, so it can be factored out, but it is a vector. When you factor it out, you still put it on the left, on the right. You cannot move it to, say, the left, because that's going to make the product non-conformable. So factoring out is allowed for matrices, but you're going to have to keep the order of multiplication. When it's on the right, it stays on the right when you factor it out. So what we got is here. And now we are really close to the solution. Notice that this is a k plus 1 vector, column vector. And the transpose of it is a k plus 1 row vector, or in other words, it's a 1 by k plus 1 matrix. So therefore, this product is actually a k plus 1 by k plus 1 square matrix. It is a square matrix. When you add up the square matrix, you still get a square matrix. These square matrix, if we assume that it is invertible, then we can multiply the inverse of that matrix on both sides of the equation. The equation should still hold. That's exactly what we do here. We multiply the inverse of that matrix on both sides of the equation. So the equation still holds. And the inverse times this matrix equals identity. And identity times anything equals that thing itself. So on the left-hand side, we have the beta vector. And on the right-hand side, we have the inverse of the sum of xi vector prime times the sum of xi vector times yi. That is our solution. So that is the ordinary least square estimator. Okay, so that is the formula for the ordinary least square estimator. We solved it easily by using some matrix manipulations. Maybe if you are not familiar with matrix manipulation, maybe you wouldn't call this easy, but once you get familiar to it, you find it's really not difficult. Whew, right? So, all right, to sum it up, we want to estimate the beta vector in the linear regression equation using a random sample like this. We introduced the ordinary least square estimator that is a solution to this minimization problem where we're minimizing the sum of squared residual, sum of squared approximation error for using a linear function of x to approximate y. We solve these first order conditions to this minimization problem and find that the OLS estimators is given by this formula. Well, is this estimator a good estimator? It depends on the context. We're going to talk about whether this estimator is any good in the next lecture.